Inget annat skål.
Machines do work, and to do this they need a supply of energy. One way of getting energy to a machine is to connect it to an overhead line shaft. This was done in the early days of industry, and you can still find some machines driven from a line shaft today. But how do you get energy to the line shaft? Well, you could use a steam engine, like this one. It's been running for over 65 years, and it was looked upon with pride and affection by the engineers who built it. They named the high-pressure cylinder Hilda, and the low-pressure cylinder they christened Alice. The engine is driven by steam, which is generated in a boiler. Steam is raised by burning coal in this firebox. What we're doing is converting energy stored in the coal, chemical energy, into a more useful form, mechanical energy. This factory converts chemical energy to mechanical energy on the premises, so obviously it has to keep a supply of fuel on hand. But now we've come to a place where they burn the same fuel, coal, on a very much larger scale. Here, the end product will be not mechanical energy, but a different form of energy, one that can be distributed much more conveniently. Can you guess what it is? Well, here's the coal being brought in by conveyor belt. It'll be ground to a fine powder, mixed with hot air, and blown into a furnace like this one, where it's burnt. The heat produced in the furnace is used to generate steam, just as it did in the steam engine. The steam drives a turbine, and the turbine drives, you guessed it, we hope, an electrical generator. The chemical energy in the coal has now been converted into electrical energy. One great advantage of electrical energy is its ease of distribution. The output of this power station is fed to a system of cables known as the supergrid. The voltage is extremely high, about 400,000 volts, and the cables are carried on pylons all over the country. Here it reaches a substation where the voltage is reduced. This happens in a transformer. The output of this transformer is at about 130,000 volts, a reduction of 2/3. Now the cables go underground to another transformer where the voltage is reduced again. Here it goes to the area electricity board at 33,000 volts. And the board supplies it to this factory at an even lower voltage, 11,000 volts. The factory has a meter to measure the amount of electrical energy it uses. kWh means kilowatt hour. It's the unit in which we measure the electricity consumed. These circuit breakers can isolate the whole factory from the supply. This factory has its own substations where the supply voltage is further reduced to 415 volts. This is the secondary or output side of the transformer. The electrical energy is distributed from here into the workshops where it is used. A main switch can cut off the whole workshop from the electrical supply. And the electricity is distributed within the workshop via distribution lines, or bus bars as they're called. The overhead bus bar is connected to an isolator on the machine. And an electrical motor on the machine converts the electrical energy into mechanical energy to do whatever work we need done. We can convert electrical energy to light energy. We can use it to light the place. Does this suggest another way we could use electrical energy? This student is doing mechanical work on a bar of steel. But he could use electrical energy to do the same job by means of the electric motor on a power hacksaw. When electrical energy is converted into mechanical energy, all the operator has to do is keep a watchful eye on things. Here's a completely different way to use electrical energy. The work is held between two copper electrodes and a high current is passed through the work. Now the work offers a relatively high resistance to the electrical current, and as a result, heat is produced. Enough in this case to make a weld. Electrical energy is often converted into heat energy, as in this application, spot welding. Yet another application for electrical energy. This crane makes use of the magnetic effect of an electric current. It's used for loading scrap steel into a hydraulic baler. Electrical energy is converted into magnetic energy, which we can use to pick up the scrap steel. One advantage this has over a mechanical grab is that the electromagnet can be set so that it can only pick up a certain amount. This particular one can't pick up more material than the baler will cope with. Could you use the magnetic effect of an electric current to pick up any kind of scrap metal? Now these are steel screws hung on wires. For the process they're about to undergo, they have to be cleaned. The process will involve what's called direct current. The negative terminal of the DC supply is connected to this brass rod, which is positioned over a chemical bath. The positive terminal of the DC supply is connected to another brass rod positioned over the same bath. From this hang long pieces of copper, called anodes, immersed in the bath. The screws are now put into the bath, hanging from the rod connected to the negative terminal. The current is switched on and something begins to happen. an electrochemical reaction starts up in which metal is transferred not as it appears from the screws to the copper, but from the copper to the screws. When the current's switched off, the screws can be taken out of the bath. They are now plated with copper. Another bath, but this time, instead of the anodes being copper, they're nickel. Again, the screws are hung from a rod connected to the negative terminal of a DC supply. This time, nickel is transferred through the bath from the anodes to the screws. Now they're plated with nickel. This process, electroplating, relies on the chemical effect of an electric current. This is another one of many ways in which electrical energy can be used in industry. Now it must be possible to disconnect any electrical installation automatically from the supply. These circuit breakers will automatically trip in the event of an overload. Another way of protecting a circuit is to use a fuse. Here's a fuse box which protects all the circuits in a particular part of the factory. This type of fuse is known as a cartridge fuse. To find out what a fuse does, let's look at a simple circuit. In one part of it, we've placed a length of fuse wire. This fuse wire has been carefully chosen in relation to the amount of current the circuit is intended to carry. The fuse wire is usually of smaller cross-section than any of the other conductors in the circuit. Let's pass a high current through the circuit and see what happens. Like all conductors, it offers some resistance to the flow of current, and that resistance causes it to heat up. The higher the current, the hotter it gets, until eventually it melts and breaks the circuit. This is how a fuse works. Now let's see a fuse in action. We've set up a power tool in such a way that we can increase the mechanical load on the motor by tightening up a vise on a steel shaft fixed in the chuck. Let's tighten up the vise and see what the effect is. When we stalled the power tool, the fuse blew and the circuit was broken. But what would have happened if there'd been no fuse in the circuit or a fuse of too high a rating? Let's put in a thick piece of copper wire. Again, we'll overload the motor of the power tool. The copper wire is apparently unaffected. The motor completely stalled. As a result, a very high current is passing through the motor windings. This will cause them to heat up, and we may destroy the motor. It's extremely dangerous not to have a fuse in a circuit, and it must be a fuse of the correct rating. The fuse will also protect the wiring of the rest of the circuit. See what happens when we pass a high current through an insulated cable. This could cause a serious fire. Fuses are essential to protect electrical motors and circuits against damage through overloading. But now let's turn to another safety measure, this time to protect the user of electrical equipment. We're going to test this soldering iron to see if it's safe to use. To do this, we use an instrument which measures the resistance of materials to an electric current. It should be very easy for current to flow between the earth pin on the plug and the metal casing of the soldering iron. The resistance should be very low. And on the bottom scale of the meter dial we read less than 1 ohm. That's okay then. it should be very difficult for current to flow between the earth pin and the live pin on the plug. The resistance between these two should be very high. We read this resistance on the top scale. It is high, almost infinitely so. This iron is safe to use. Now let's carry out the same tests on another soldering iron. Remember, between the metal casing of the soldering iron and the earth pin on the plug, the resistance should be very low. Again, we read this on the bottom scale. Again, it's well under 1 ohm. That's okay. Now, we want to find a very high resistance between the live pin and the earth pin on the plug. This resistance we read on the top scale. And look at that, the needle has gone the wrong way. Very low resistance between earth and live means that there's a fault in the soldering iron. And here it is. The wire connecting the live conductor to the heater element has lost some of its insulation and is able to touch a metal screw that's in contact with the casing of the soldering iron. This soldering iron could represent a serious hazard to the operator. Here it's being connected up to live and neutral terminals of an electrical supply. The brown conductor is live, the blue conductor neutral, and the earth conductor, which is green and yellow, isn't connected to anything at all. When we switch on, all the metal exposed parts of this soldering iron are alive. Anyone who picked it up by any metal part would be in for a shock. It's now a very dangerous piece of equipment. But we can protect ourselves from hazards like this by making proper use of the green and yellow earth conductor. It's connected to all the exterior exposed metal parts of the soldering iron. And the earth continuity conductor is wired to this pin in the plug top and via this socket outlet is connected to earth. Now here's a faulty iron which we've wired up in the correct way. This is the green and yellow earth conductor. Any fault current will now go this way, straight to earth. The neutral conductor is on this side. It's an insulated cable coloured blue. And on the live side of the circuit, instead of the brown live conductor, we've put in a fuse. Now let's switch on and see what happens. The fault current goes to earth and blows the fuse in the process. The operator knows that something is wrong. By the way, just in case you think we've been risking our lives with mains voltage to bring you this demonstration, the live and neutral terminals in this socket outlet were wired up to a battery. Why do you think we didn't put a fuse in the neutral conductor as well as the live? And since we put a fuse in only one conductor, why did we choose the live conductor?